Hey my friends, and welcome to my lecture on modulation. This concept is very easy and super useful in communication systems. Let's say we want to send information from a transmitter to a receiver. Xt is the message or the information that we want to transmit from one point to another. The Fourier transform of xt is x omega, and let's assume the maximum frequency in the frequency content is omega m. The length of antenna in the receiver side is inversely proportional to the maximum frequency. The explanation behind this relation comes from a concept called beamforming, which is an advanced topic in array signal processing and beyond the scope of this course. So keep this in mind. To effectively receive information using an antenna, the length of antenna should be inversely proportional to the maximum frequency of the transmitted signal. What does this mean? This means if omega m is small, the antenna must be large. What is the problem in this case? The problem is, in order to effectively receive information with low omega m, the length of antenna, or technically the size of your phone, must be large. So instead of carrying a small cell phone around, you need to carry a ridiculously giant cell phone. That's why the modulation is used to make small antennas feasible by shifting omega m to higher frequencies. Let's see how modulation works. If we multiply xt by this complex exponential function, we get this. From my lecture on Fourier transform tables, we know if we multiply xt with this complex exponential function in the time domain, x omega gets shifted by omega c. This is called frequency shifting property. Now let's back to our example where the maximum frequency in x omega is omega m. When we multiply it by this complex function, x omega gets shifted by omega c. This means 0 goes to omega c and omega m goes to omega m plus omega c. Here we go. Now think about it. Why this is useful? If we transmit xt itself, length of antenna in the receiver side is inversely proportional to the maximum frequency or omega m. Now, if instead of xt, we transmit xt multiplied by this complex exponential function, length of antenna should be inversely proportional to this, which is the maximum frequency here. So, if omega c is very large, the length can be very small. That's one of the main applications of modulation. Let me recap what I've said so far. By multiplying xt with this complex exponential function, where omega c is usually a very large number, we shift the maximum frequency in x omega to a much higher frequency. This multiplication is usually referred to as modulation. Now, instead of xt, if we transmit this signal over the channel, on the receiver side we can effectively receive information with a small antenna. Let's see the whole picture in the communication systems. First, we multiply xt or information by this complex exponential function. Again, this multiplication is usually referred to as modulation. Then, we send it over a communication channel. Basically, the media between transmitter and receiver is called channel. Let's assume the channel adds no noise or distortion and we get the exact same thing on the other side. This channel is called ideal channel. In the next lecture, I will discuss non-ideal channels and we will learn how to use equalization to deal with them. For now, let's assume the channel is ideal. After receiving information, we are just interested to know xt, which is the desired information. In fact, xt is the main message that we want to send from transmitter to receiver. What does this mean? It means we need to get rid of this complex function. To do so, we just need to multiply it by another complex function with the negative power. Now the exponential terms cancel out each other and we end up with the main message or xt. This multiplication, which happens on the transmitter side, is called modulation. And this multiplication, which happens on the receiver side, is called demodulation. This signal is usually referred to as a carrier signal, as we use it to carry information from one point to another. and omega c is called carrier frequency, which is usually a very large number. Here is a simple explanation of the whole system. We have a message that we want to send from one point to another. We give that message to a carrier whose job is to carry the message from the transmitter to the receiver. At the receiver side, we are just interested in the message, not the carrier. So we need to extract the message from its carrier. The act of putting information on the carrier is called modulation, and the act of removing information from the carrier is called demodulation. One of the problems here is the fact that we are working with complex functions in both sides. In practical applications, we don't like complex numbers. That's why the complex function is usually replaced by cosine or sine function. Let's see how it works. Based on what we learned so far, we multiply xt by this complex function and then we send it over the channel. On the other side, we multiply it by another complex function with negative power to recover the message, i.e. xt. Now let's replace these complex functions by cosine functions. The same story. This is our message and this cosine is the carrier signal. The act of putting message on the carrier in the transmission side is called modulation, and the act of extracting the message from the carrier in the receiver side is called demodulation. Let's see how the system works. For simplicity, I'm going to consider the same example where the maximum frequency is omega m. Let's call this signal ZT. If we assume the channel is ideal and adds no distortion, we receive the same signal on the other side. Also, let's call this signal R of t. To analyze the whole system, let's start from Z of t. Zt is basically xt multiplied by cosine omega ct. If we travel to the frequency domain, the Fourier transform of xt is x omega, and the Fourier transform of cosine function based on my lecture on Fourier transform tables is this. Also, we know multiplication between two functions in the time domain is convolution in the frequency domain. So here we have convolution. Don't forget about 1 divided by 2 pi. Pi is cancelled by pi. Also, as we've seen many times in the past lectures, to do convolution with a shifted delta function, we just need to shift x omega. So if we convolve x omega by this delta function, we get this. The same story for the other convolution. Don't forget 1/2. So this is z omega. Let me clean this section and write it here again. Now let's plot z of omega. To plot this term, we just need to shift x omega by omega c to the right. So 0 goes to omega c and omega m goes to omega m plus omega c. To plot this term, we need to shift x omega by omega c to the left. So 0 goes to minus omega c and omega m goes to omega m minus omega c. Here we go. Don't forget this 1/2. So if the maximum value in x omega is 1, for example, the maximum value for z omega is 1/2. Let's step back and see the big picture before continuing. The act of putting information on the carrier signal, i.e. cosine function in this case, is called modulation. As we showed before, when we modulate the message, i.e. xt, with a complex exponential function, we shift the frequency content to higher frequencies. Here's the same story. When we modulate xt with cosine, again, we shift the frequency content to higher frequencies. So the mission is the same. The difference between modulation with a complex function and cosine function is the fact that we got 2 copies here and the amplitude is also becomes half. Now let's continue. If the channel is ideal, we receive the same zt on the other side. Now it's time to extract the message from its carrier. To do that, we multiply it by another cosine function. So RT is basically ZT multiplied by cosine omega CT. Again, multiplication in the time domain is convolution in the frequency domain. So in the frequency domain, we get this, where z omega is the Fourier transform of zt, and this is the Fourier transform of cosine function. Pi is cancelled by pi. Now, if we convolve z omega by the first delta function, we get this. And this convolution results in this term. Here, we express r omega in terms of z omega, but we are interested to see the relation between r omega and x omega, which is our message in the frequency domain. To find the relation, we just need to use this equation. That's it. To find this term in terms of x omega, we just need to use this equation and replace all omegas by omega minus omega c. So we get 1/2 x omega minus omega c. Minus omega c is minus 2 omega c. Plus, here minus omega c is cancelled by omega c, and we get x omega. The same story for this term. We just need to use this equation and replace all omegas by omega plus omega c. So plus omega c is cancelled by minus omega c, and we get x of omega. And also plus omega c plus another omega c, we get this. Don't forget about this 1/2. Here you can see r omega in terms of x omega. Let's simplify it by factoring out this 1/2 and multiplying that by the 1/2 outside the parentheses. So we get 1/4 x omega minus 2 omega c. There are 2 x omegas, so we get 2x omega plus x omega plus 2 omega c. Let's bring this coefficient in and write it here. Here's what we get. Let me clean this part and write it here again. Now let's plot r of omega. The first term is x omega, which is shifted by 2 omega c to the right. So 0 goes to 2 omega c and omega m goes to omega m plus 2 omega c. Also, the amplitude is 1/4. To plot this term, we need to shift x omega by 2 omega c to the left. So 0 goes to minus 2 omega c and omega m goes to omega m minus 2 omega c. The amplitude is again 1/4 of x omega. Finally, this term is x omega itself, just the amplitude is 1/2. This signal is r omega, which is what we get after demodulation. Let's step back again and think about what we are doing. We basically want to recover the original message, i.e. xt, in the receiver side. If you compare the frequency content of x omega with r omega, this part is the same, just the amplitude is different. But these two copies are extra, or basically undesired. To recover x omega, we simply need to use a low-pass filter. Let's call it h of t. We use this low-pass filter to pass the desired component and reject the other ones. Let's call the output yt. Yt is basically rt convolved by ht. In the frequency domain, convolution is replaced by multiplication. So the low-pass filter will pass this desired section and reject the other copies as h omega, or frequency response, is 0 in those intervals. To compensate 1/2, the frequency response should be 2 here. So y omega is r omega multiplied by h omega. So this part is multiplied by 2 and we get this. This part is multiplied by 0 and therefore gets rejected by the filter. The same story here. So this is our y omega. By comparing y omega with x omega, we can conclude that they are equal. Therefore, they must be equal in time domain as well. Yt is equal to xt, which means we recover the original message which was sent by the transmitter. Let's recap the whole story. Xt is the message that we want to transmit. We modulate the signal, then send it over the channel, and demodulate the received signal. After demodulation, we got 2 extra copies which are not desired, and also the amplitude of the desired section is 1/2 of the original signal. That's why we use this low-pass filter to reject the undesired components and compensate the amplitude. By doing that, we recover the original message. That's it. To make sure you fully understand modulation with cosine function, I'm going to show you a fun example. First, I will play a song, then I will do modulation and demodulation to see the impact on the frequency content. Finally, I will use a filter to recover the original song. Let's start with the song. To take a break as I'm playing the song, I will show you a short video on my trip to Caltus Lake. Here's the song in the frequency domain. Now I modulate it with a cosine function. Here's the modulated song in the frequency domain. As you can see, modulation with cosine function shifts the frequency content to the higher frequencies in both directions. Also, the amplitude of each copy is half of the original song. Let's listen to the modulated song. It's annoying to listen to this signal as it just includes high frequency content. Now let's do demodulation with the same cosine function. Here is the demodulated signal in the frequency domain. We see two extra and undesired copies on the left and right with 1/4 of the amplitude. Also, the amplitude of the central section, which is desired, is half of the song. Let's listen to the demodulated signal. You can clearly hear the song, but there is also noise due to the undesired copies. Finally, we use this low-pass filter to compensate the amplitude and reject the undesired copies. Here's what we get. Let's listen to it. As you can hear, this is the original song with no distortion. That's it. Let me explain another beauty of modulation. Modulation is one of the techniques that makes it possible to have several radio stations transmitting information at the same time. For example, let's say this radio station is broadcasting sport news. At the same time, this boring guy is talking about economy. At the same time, this guy is talking about politics and BS. As you can see, they all transmit information at the same time. And what we receive is basically the mixture of all of them. So how come we can just listen to one radio station and remove the rest? Modulation is the key. Let me elaborate that more. For simplicity, let's say we just have two radio stations working at the same time. The message from the first station is x1t, which is like this in the frequency domain. The message from the second station is x2t, which is like this in the frequency domain. These shapes are selected just for simplicity. Now, if the first and second stations transmit their message over the channel without modulation, we get a combination of both messages at the receiver side, i.e. x1t plus x2t, which is like this in the frequency domain. As you can see, they are not separable in the frequency domain. Therefore, we cannot distinguish x1 from x2. Now let's add modulation to the game. The first station modulates x1t by cosine omega 1t. As we already discussed, this multiplication shifts the frequency content of the message by omega 1 to the left and right. At the same time, the second station modulates x2t by cosine omega 2t. Again, this multiplication shifts the frequency content of x2 by omega 2 to the left and right. Now the radio stations transmit the modulated signals over the channel. On the receiver side, we get the combination of both signals again, but here is the beauty of modulation. In the frequency domain, we get this one plus this one. Here we go. So, as long as omega 1 and omega 2 are sufficiently different, the messages are separable in the frequency domain. Therefore, we can easily use a filter to pass one message and reject the other one. Okay, that's all I want to say for modulation. I just want to say many thanks for watching my tutorials over the past few months. Honestly, I've been super busy, but the comments that I got from you give me the energy to sleep less and work harder to make more videos. Please don't forget to subscribe to my channel and keep commenting if you have any feedback or questions. You're just awesome. Thanks again and see you in the next video.